So in the last two videos, we defined the chain group CRK for an abstract simplicial complex K and the differential D from CRK to CR-1K. But to actually produce a chain complex, which is what we're supposed to be doing, we need an extra thing. We need to prove that D squared is 0. So that's what we're going to do in this video here. So there's the proposition. D squared is 0, or more precisely, if we look at the composite from, you do a D from CR plus 1K down to CRK, and then another D from CRK down to CR minus 1K, then that should be 0, so that we get a chain complex. And we're going to discuss the proof, at least first, for the case R equals 4. So typical generator for the group C4K corresponds to things V0 up to V4, where that's some simplex of the some 4 simplex of the complex K, which we're going to write just as 0, 1, 2, 3, 4 in the usual kind of abbreviated notation. And the claim's got to be that D squared of U is 0. So we need to do D twice. So firstly, let's just do D once. So we get du is this thing here. We omit the 0, get 1, 2, 3, 4. Omit the 1, you get minus 0, 2, 3, 4. Omit the 2, you get plus 0, 1, 3, 4. Omit the 3, you get minus 0, 1, 2, 4. You omit the 4, you get a plus 0, 1, 2, 3. So now we need to apply d to each of these things to get d squared u. And we're going to lay this out as follows. We're going to have 5 columns, one for each of these terms, and then each of these you're going to get 4 terms in d of it, which we're going to write as a down the column. Okay. So in this first column here, we've got d of 1, 2, 3, 4. So we omit the 1, we get a 2, 3, 4. Omit the 2, you get a minus 1, 3, 4. Omit the 3, you get a plus 1, 2, 4. Omit the 4, you get a minus 1, 2, 3, and so on. And then and then the second column, you've got d of minus 0, 2, 3, 4. Okay, so we omit the 0, so that would normally occur with a plus, but because we've got this extra minus here, it occurs with a minus, so you get a minus 2, 3, 4 there. Omit the 2, that would normally be with a minus, but now it's with a plus, so that's a plus 0, 3, 4, and then you get a minus 0, 2, 4, and a plus 0, 2, 3. And similarly, the terms in d of 0, 1, 3, 4, they appear in this column, d of this term in this column here, and d of the 0, 1, 2, 3 is written down in that column there. But now we're going to regroup these terms. We're going to do it like this. So we draw this kind of wavy diagonal blue line down the middle here, and then everything else we kind of divide up according to these red rectangles. So we've got to one group here, 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 and so on. And we observe that everything in this rectangle here cancels against everything there, right? You've got a plus 2, 3, 4, minus 2, 3, 4, minus 1, 3, 4, plus 1, 3, 4, plus 1, 2, 4, minus 1, 2, 4, minus 1, 2, 3, a plus 1, 2, 3 there. So everything in here cancels everything in here. Similarly, everything in here cancels against everything in there. Everything in here cancels against everything in there. And then finally here, you've just got a plus 0, 1, 2, cancelling against the minus 0, 1, 2 there. So when we add everything up to get d squared of u, I mean, remember we started with du is like this, and then d of the 1, 2, 3, 4 is appearing in this column. D of the minus 0, 2, 3, 4 is occurring in this column. So to get d squared u, we just have to add up everything in this in this kind of matrix here, and everything cancels in the indicated groups. So we get d squared u is just 0. So that proves what we were supposed to be proving, that this d squared is 0, at least in this case here, where we start with C4K. But now let's discuss at least how the proof is going to work for a general R. Okay, so you've got you start with your 0, your u, which might as well be a 0, 1 up to R. Of course, it might be a sum of terms like that, but we can just treat each term individually. Okay, so what happens when we take d squared of this, right? You're going to get r times r minus 1 terms. I mean, actually, that's wrong. That should be r plus 1 times r. Never mind. But firstly, there's r plus 1 entries in u, so we get so at the first stage when we just take du, there's r plus 1 terms in that, and then when you apply d to each of those terms, you get r terms coming out of that, so you get r plus 1 times r terms altogether. when you first do the first D, you get a bunch of terms where you've just left out one of the entries in this original U. And then when we do D squared, we get a bunch more terms where we leave out another entry. So each of these terms in this array, each one is just like this 0 up to R, but with two of the terms, say I and J, omitted. Okay. So how can we get the term with I and J omitted? It turns out you get it in two different ways. I mean, you can kind of omit the J first, or you can omit the I first. Okay, so here we're sort of we're labeling these with the I, with I and J missing the I less than J. Okay, so one thing that can happen is you omit the J first, and then you omit the I. Or you can omit the I in the first application of D, and then you omit the J in the second one. Now, the term of type A, okay, it's going to appear with a sign of -1 to the I plus J, right? You get a -1 to the J because you omitted the J in the first place, and then you omit the I, and that has a sign of -1 to the I, so you get -1 to the I plus J. Okay. And you might think, if you were a little bit too hasty, that you also get a -1 to the I plus J for the second term, but that's not quite right, because here, remember, I is less than J, so we omit I, okay, so that comes with a sign -1 to the I, but then you're going to omit the J, but the J has moved left by one place. So it doesn't occur with a -1 to the J anymore, it appears with a sign -1 to the J minus 1. Okay, so and then combining that with the -1 to the I you had already, you get a sign of -1 to the I plus J minus 1. Of course, that cancels with the appearance coming in case A. Okay, so signs are opposite, everything cancels, and we see that D squared is 0. And that means that we've got a chain complex. Remember, that's the definition of a chain complex, a sequence of abelian groups, homomorphisms between them from AR to AR minus 1, with a property that D squared is 0. We've now checked that D squared is 0, so these groups CRK are assembled into a chain complex. And as with any chain complex, it's going to be interesting to consider the homology. Let's remember how that goes. So we define ZRK, the group of cycles, to be the kernel of D. So that's the stuff in CRK which is sent by D to 0. And then we quotient out by the image of D from CR plus 1K to CRK. That's called BRK, the group of boundaries. So the condition D squared equals 0, that ensures that BRK is contained in ZRK. So it's meaningful to form this quotient group ZRK mod BRK, and that's what's called the homology group HRK of our simplicial complex.